Dear participants, dear colleagues and friends, dear Professor Barry Sanders, good evening everyone in our time frame, and good morning in Professor Barry Sanders' time frame. So it is my pleasure to welcome all of you in our last session for today of our summer school, Quantum Horizon Developments and Opportunity, which we organized to provide young, motivated people a concise, conceptual introduction to the current topics of quantum science and technology. It is my distinct pleasure to inform you that our speaker in this evening is Professor Barry Sanders from the University of Calgary in Canada, a distinguished physicist and world-class expert in the field of quantum science and technology. He is also part of TÜBİTAK Research Institute for Fundamental Sciences as a distinguished associate member, which is a pleasure and honor for us. He's going to give a great lecture entitled On Quantum Computing. Professor Barry Sanders is especially well known for his seminal contributions to theories of quantum limited measurement, highly non-classical light, practical quantum cryptography, and optical implementations of quantum information tasks. Professor Barry Sanders has many awards. In particular, he's a fellow of the Institute of Physics in United Kingdom, the Optical Society of America, the Australian Institute of Physics, the American Physical Society, and the Royal Society of Canada, and so on. In 2016, he was also awarded the Imperial College London Doctor of Science degree. At this point, I want to invite Professor Sanders to the stage to begin his talk. Barry, we are absolutely thrilled to have you with us. Thank you so much. Please begin your talk or lecture.
Thank you very much, Ali. I'm just checking you can hear me fine, right?
Mm-hmm.
Okay, great. Yeah, it's a great pleasure to be here. I wish I have the opportunity to visit in person. I would love to come over, but being able to talk to you all virtually is second best pleasure. So thanks. I don't know everybody's background in quantum computing, so the purpose of this presentation is really to convey what I think quantum computing is about at all levels. So I just want to take under an hour to share with you about quantum computing. And then the subtitle says Principles of Classical and Quantum Computing. So I always believe that to really understand quantum computing, we need to understand computing. And we all use computers, but we might not necessarily understand the principles underlying them, and yet it's important to do so, because a quantum computer in the end is just a computer. And also to claim that a quantum computer has advantages needs a fair comparison with non-quantum computers. So I'll just go into it. Of course, I can't cover everything about quantum computing in under an hour, but I'll cover some key points. Okay, so this is just the contents. I'll just give you an introduction to various concepts, then I'll talk about quantum computing. I'll talk about algorithms and then robustness. And actually, I'll move on from robustness of quantum computers to the practical implementations. On the right, that's a picture of Calgary where I am. So you can see the Rocky Mountains in the background. Nice place to be. And you can see lots of ways to reach me on social media. Okay, so let me just cover first some basic concepts of computing. These look basic. I'm just going to go through each one just to make sure that we know what they mean. And I'll comment a little bit about how they connect with quantum. So first of all, what is computing? And computing is really activities using a computer. So a computer is a machine that performs arithmetic and logic operations, and computing is what we can do with that machine. That's how it works. And then a universal computer goes further. A computer can be a purpose-built machine, like an abacus, to do arithmetic. A universal computer is programmable. So it means that you can conceive of every machine that would perform arithmetic and logic operations, and a universal computer can simulate what every purpose-built computer can do. And then there's strong and weak principles. Weak principle is that a universal computer can simulate what any computer can do, and a strong equivalence would be that a universal computer can do so efficiently. And by efficiently, it means whatever the costs there are in a purpose-built machine, the universal computer can do it with no more space, time, and other overheads than scale with a polynomial function of those resources. And resources can be a lot of things. And in fact, in order to assess how good a quantum computer is, we really need to look carefully at all kinds of resources, because sometimes there are claims of advantages with quantum computers that don't stand up to scrutiny. And as examples, we care about memory. So there might be memory considerations, and memory can come in different forms. There's random access memory, there's disk memory. So there's different types of memory we use in a computation, and each of those has to be studied. Time, and then to physicists, time is, a basic concept we do. Time is the parameter for evolution in the universe. But in computing, even figuring out what time means, is it wall time, that is the time that passes for us between the beginning and end of a computation, or is time the CPU time, or is time, and I'll get into it a bit later, is time the depth of a circuit that represents or that executes the algorithm, and on and on. And I'll talk a little bit about that. Randomness is also key. In computing, there's a separation between deterministic computing and probabilistic computing. And for quantum computing, necessarily because of the probabilistic aspect of measurement, there is randomness built in. So we have to compare, we have to be careful in comparing to classical computing to make sure we're not just getting advantages out of random number generation that could arise out of measurement. And we have to study all this stuff. But usually in quantum computing textbooks, we focus on time, which is often represented by something like the number of gates, and space would be the number of qubits, but there's more things going on. And then complexity, this resource scaling aspect, is the question of how much resource do we use. And so we'll typically think about how many bits for the input. So a computer accepts bits going in and it yields bits going out. And then the number of bits going in that specify the instance of the problem and the program. So, if we want to factorize a number, we might consider how many bits it takes to represent the largest number we're going to factorize on our machine, and the program and whatever else, that's the number of bits. And then we want to know how the resources scale. And if the resources, for a universal computer, if the resources scale no more than polynomial in the number of bits, then that universal computer is an efficient simulator. So it's strongly equivalent. So basically it's an efficient simulator of any machine. And if it doesn't scale that way, then it's not efficient. And then we care about robustness. And in quantum computing, there's a division between how a quantum computer person talks about robustness and how and I'll just say classical computer, so in computer science, how robustness is talking about it. Robustness in computing, not quantum computing, is about coping with all kinds of problems. I/O is input, output, there's execution errors. And so we look at that. In quantum computing, we often tie the discussion to quantum error correction and what we define in quantum computing to be fault tolerance. As quantum computers are becoming more and more commercial, and by commercializing them, they're not just theoretical tools that we test in the lab and write papers about, but they actually have to compute for customers. At the moment, commercial quantum computers don't necessarily compute very well, but but they have to be able to do it. And so there's a collision going on between the robustness required for real world computing versus robustness that physicists tend to define as being the measures. Okay, so I'm just gonna talk about so what I think are the essential basic concepts we need to know classically to then understand quantum computing. And for this, I'm building into my story reversible computing. Now, on the left, this is the Boolean. On the right, it's reversible. And historically, reversible computing was a big deal in the 1960s. It came out in theoretical physics as another step in understanding Maxwell's demon. There was Landauer's principle that the heat generated by Maxwell's demon would come by erasure. And then there were arguments from people like Charlie Bennett, Toffoli, and others that said, what if we don't erase? And so theoretically, the question of where is the fundamental irreversibility in Maxwell's demon was a driver of reversible computing. And in the practical sense, and IBM was a big player in this in the 60s, 70s, the question of can we reduce the heat generation in a chip? And that becomes very important because heat generation can limit us to two-dimensional computer chips instead of three-dimensional and other things. So reversible computing was driven by the twin ideas of the fundamentals of Maxwell's demon and the practicality of trying to eliminate heat as much as possible in order to scale up computers. And my way of thinking about quantum computing is reversible as a key bridge. So certainly when I teach my students quantum computing, I spend time on reversible computing as a step towards grasping quantum computing, but that's not in the textbook. So what I'm saying is a little bit unorthodox in pedagogy. So on the left side, it's about Boolean logic. And the idea is that every state, and I'm not using state in a strict computer science sense, more like a physics sense. So the state is just a string of bits, and there's bits going in. The state could be involved in the program, it might not. But if we just think of this state S as being the input instance to a problem related to factorization. Now, factorization typically it's not a decision problem. Factorization might be, give me all the prime factors of some large composite number or something like that, but we can turn most computational problems into decision problems. So instead of asking for the factors of 15, I can say, is 2 a factor? Is 3 a factor? I can convert them to decision problems. And decision problems are ones that map the string of bits S into a bit, 0 or 1. And so mathematically, a decision problem is a Boolean function, just maps a string of bits to a single bit. And in order to, typically we'll assess whether there are advantages in quantum computing based on formulating decision problems. So if you ever see these complexity diagrams, they're related to decision problems. Most things that we want to compute are not decision problems, but if there's an efficient reduction to a set of decision problems, then it's very useful to do this. And the nice thing about this, mathematically, we can show that we can reduce it down to a set of Boolean operations. And then if I really want some hardcore comparison of classical and quantum computing, I'll reduce this down to a NAND tree. NAND is not AND. So it turns out that the NAND gate is universal for Boolean logic. And then in the diagram below, you can see an input. It's got XZ, XY going in. And then the NAND gates are 2 to 1. They're not reversible logically because 2 bits go in, 1 bit comes out. So they're inherently erasing. But we can take any Boolean function, write it as a parallelized set of NAND operations on the bits, and then the output F on the right is a single bit. That's the answer to that problem. And then what is time in this? Well, the way it works, the way we define time in computing in a way that we can study rigorously the resource requirement is we'll define it to be the largest depth of the shortest circuit. And so here the depth in that diagram is, you can see X going in. So input is 1 time step. Then you see the first parallelized step where 2 NAND operations take place, the next time step with 1, the next time step with 1, and the final readout of F. So the depth of the longest cycle is 5. You can see that Z effectively goes through just 3 or 4. So then there might be other circuits to execute the Boolean function, but it's so time is the largest depth of the shortest circuit. And so it's, even in order to figure out how much time it takes to solve a problem itself can be an optimization problem, which is considered hard, typically NP hard in computing. So time has a whole different meaning in computing than what we're used to as physicists. And yet this is something important to consider in comparing classical to quantum computing. Now, mathematically, it turns out that we can embed every decision problem into a permutation. So we take that string S and the result, let's call that f of S. And then if we map S and f of S to, we consider the string S and the bit 0 going in and the string S and the result f of S coming out, we can then write every circuit as permutations. So we're able to replace Boolean logic by permutations that have the same number of bits going in as going out. And this idea of embedding Boolean functions as a reversible operation was the key in studying the logical conclusion of Maxwell's demon. If you eliminate erasure, then you can see that the entropy is, really tied to memory, and the memory in reversible computing is about storage of all the junk that you would just love to erase. And that's what Maxwell's demon has to store. So we can model Maxwell's demon as a reversible computer. And then when we do that, just as on the left, we can decompose to cycles of parallelized NAND gates. Instead, we can decompose the permutation. This goes into some mathematics about permutations as compositions, permutations, the kind of stuff I probably, your side too, we learn in high school where we take permutations and break it down. And so using that kind of math, but more sophisticated, we have a number of choices. And so in the diagram at the bottom right, you can see 3 bits going in, then there's a gate and 3 bits going out. There are different examples. And so on the lower left of that right diagram, you can see 3 wires going in. Each wire corresponds to a bit, and then there's that filled in dot is a control operation. And so what you see on the lower left is a control not. And it says, if the first 2 bits are both 1, flip the 3rd bit. And otherwise don't flip the 3rd bit. And then the first 2 bits don't change. And this is the Toffoli gate, control not that we use in quantum computing, but its origin was by Toffoli was in reversible computing. And then on the lower right, you can see a different one, which says, if the first bit is 1, swap the 2nd and 3rd bit, otherwise don't swap. And that controlled swap is known as a Fredkin gate. In fact, historically, the very first proposal for a quantum version of computing that would, the proposal for an experimental realization, that was 1989, 2 papers in parallel, one by Yoshi Yamamoto and collaborators that appeared in a Asia Pacific conference, and the other was Jared Milburn at the University of Queensland back in 1989 when I was his postdoc. So I kind of got hit. This result means a lot to me personally because I started working on quantum computing back in the late 80s. Of course, and that was before the mid 90s when Shor's work and others came out. So every paper got rejected that I wrote. So I have, the answer was always quantum computing would never work. So why would any decent journal publish? So I worked on quantum computing in the days when everything was rejected. And that controlled Fredkin gate at the bottom was my motivation. Okay, so that's reversible logic. Now we go to quantum mechanics. And for quantum mechanics, I'm just gonna define what it means to have quantum mechanics. And I'm sure there are people in this virtual room with far more expertise than I have, but I'll just say how I think about it, because we have to get the mapping right and think about what it means to quantize computing. So roughly, this is just a rough description. I think of every state, a state in quantum mechanics, so that S that I had before is replaced by a self-adjoint positive semi-definite operator rho, which we think is a density operator, or density matrix in the representation, acting on Hilbert space. And then for the purposes of doing quantum computing, we'll just take it as pure. So every state is idempotent. So I can write it as ket psi, bra psi, a projection. And then we don't care about every possible state. We care about representations of information. And for that, we take it to the qubit string. And so for the qubit string, once we go to pure states, I write H2 star. H2 is the 2-dimensional Hilbert space. The power of star refers to a tensor product of 2-dimensional Hilbert spaces. Each 2-dimensional Hilbert space holds a qubit. And then we can write that as, we can write every qubit as pair of complex numbers. And then the star means, it's just a tensor product of 2-dimensional vectors. And of course, normalization comes in. So we then take advantage of the projective space. Then quantum computing ideally is just a unitary map. And unitary maps are just isometries on Hilbert space. And the nice thing is that if we take reversible computing as permutations on strings, then the unitary map, unitaries are just the isometries on Hilbert space compared to isometries that we use in reversible computing. And so there's a very nice map between them. And the early history of quantum computing made use of this. And I mentioned my own history when I got into quantum computing in the late 80s. In those days, before the mid 90s developments, I spent my time thinking about how to quantize reversible computing. Okay, and then the measurement side, well, measurements to me are positive operator valued measures. And then if we make projective valued measures, we have that, the sequence of projections. The projections are orthogonal to each other, and we can write projections as being ket I, bra I, and you can see it's dual to the pure state. And in the end with quantum computing, just like we restrict all our quantum states to be qubit strings or superpositions thereof, the computational basis, we just take it to be projections onto bits. Okay, and then in this way, my view of quantum computing is what is now called end-to-end. Everything I do in quantum computing is bits in and bits out, whereas you'll see a lot of work on quantum computing, for example, linear equation solvers and stuff like that, where it's bits in, qubits out. And we always have to be careful, because if we claim advantages of quantum computing and don't get bits out, we could be ignoring some cost required for really answering a computational problem. Okay, and then the kind of gates that we get, well, I just put some examples here. So these are the quantum gates that we don't have classical analogs for. The Hadamard gate maps, and then I have ket B. B is a bit, 0 or 1. And then I just wrote B bar as the rotated basis version. So Hadamard maps 0 and 1 to superpositions of 0 and 1, where we can get a plus or minus sign. And whether it's plus or minus comes out of -1 to the power of that bit. There's a rotation gate, which takes the bit and rotates it. And by rotate, it's not rotating the qubit, it's just changing the phase of that state. So it will only matter if there's superpositions. And if B is 0, no change of phase. If B is 1, there's a change of phase. And then there's something off in the literature called magic, which is the T gate. And it's a rotation by pi4 of the qubit. And so we don't, if early on in quantum computing, back in the late 90s, there were papers about how powerful quantum computing was, and computer scientists got suspicious. They say, well, if you're using real theta, real numbers, you're not doing Turing type computation. And it was quickly realized that we don't need that. We just need one special gate out of those rotations. That's the T gate. And that's often called magic. And I don't really have time to go into a lot. The controlled knot and the controlled knot, that second one is the Toffoli gate, but a quantum version. You can see how I write it. Controlled knot just takes 2 bits, B and B prime. It'll keep the first bit the same, and then it will do a addition mod 2 of the first and second bit in the second entry. The CC knot does the same. It keeps B and B prime the same, but then the function is B prime, B double prime plus B, and the plus is mod 2. And this is related to what I said, the Toffoli gate of decomposing permutations. So in fact, understanding that CC knot and its role can be thought of as in terms of reversible computing and permutations. And then at the bottom, I just wrote the quantum teleportation circuit to just give you the idea how we use these circuits. So on the far left, instead of bits going in, this is purely quantum circuit. I'm not claiming it's a computation. And then the input for the first qubit is the state psi. The other two are state 0. The Hadamard at the bottom left converts the state 0 to a superposition of 0 and 1. Then the controlled knot that you see would flip the middle 0 to 1 only if the last qubit is 1. But of course, it's a superposition. So that generates a maximally entangled state 0, 0 plus 1, 1. And then we use that to controllably flip the psi, do a Hadamard on the result. Then you can see 2 dials, got the arc with the needle. So that measures whether the bits are 0 and 1. If this is a 0, don't apply an X, which is a not operation to this. If it's a 1, do apply the X. Here, if this is a 0, don't apply Z. If it is, apply Z. The Z operation is this rotation, but it changes the phase in front of 0 to no change. And it changes the phase in front of the 1 to a minus sign in front. And lo and behold, we recover the third qubit becomes the state psi. And that's what quantum teleportation is about. We destroy 2 qubits and make third one here. You can wonder why there's all this effort. You know, if we have the state psi, why destroy it and replicate it somewhere else? Theoretically, the work that came out in 1993 was very important because we have the no cloning theorem and the idea that somehow we can replicate the state here, but because of no cloning, have to destroy it over here was really, really important because this communication is classical. So we can think of an information theoretic context where if I say to you, send this qubit to your friend, but you have no quantum channel between you and your friend, if in advance you can share an entangled state, then you can use the entanglement in classical communication to send a qubit. So it shows us that 1 qubit equals 1 e-bit, that's a maximally entangled pair of qubits, plus 2 bits. So think of this, it's like a formula. 1 qubit equals 1 e-bit plus 2 bits. And this is the kind of analysis that we do in information theory, following from what Shannon did, others like Halevo over the years, various others. So we have a set of, we have these equalities of information, and quantum teleportation teaches us a lot about that. But that's not the purpose of this talk. Okay, now I'm going to get us back to quantum computing. So my definition of quantum computing is that it's a machine, that quantum computing is using a machine that accepts bits on the input, yields bits on the output, but can do quantum transformations in between. And again, the way I define it is not universal, that a lot of quantum computing discussion ignores the need to have bits at the end. That's fine, but if we're really analyzing the value of quantum computing, it's only half a story. And then the quantum programming a quantum computer is really about writing a circuit that executes a unitary transformation, at least in the ideal, and we can decompose it. One way to decompose it is Hadamard and Toffoli gates that I've talked about. Another way is decomposable into 1 and 2 qubit gates. We prefer 1 and 2 qubit gates because Toffoli gates are 3 body interactions, and we know from our basic physics 3 body interactions are problematic. So 1 and 2 qubit gates are the norm in the practical world. And then the universal quantum computer is considered efficient if any quantum algorithm that we write down can be efficiently executed. So if we think about the ideal resource cost to execute a quantum algorithm, then if it can be executed efficiently on a then if it can be executed on a quantum computer with at most all polynomial overhead, it's considered efficient. These definitions are not so prevalent today. As we get to practical quantum computing and we look for real value in commercial quantum computers, we tend to ignore these arguments because these arguments are very theoretical and consider asymptotic. It's kind of like saying in the limit of an infinitely big problem and an infinitely large computer, how much would it cost to execute? And then in the real world, people say, I don't care what your theory tells me. You know, how do I compare? So efficient in the modern commercial world has a different meaning. I won't go into that. Okay, and then the complexity which takes place in our ideal world is similar to what I talked about before. How much does it cost to scale up to bigger and bigger problems? And then we tend to have different kinds of scaling. If we do search problems, the famous Grover search, we have a provable quadratic speedup. So we care about polynomial scaling. On the other hand, if we take Shor's algorithm, which is not a provable advantage for factorization, but it's believed with good reason to be what's called sub-exponentially better, so it's not quite exponential, but better than any polynomial, then we have our scaling, we have a strong belief that it holds, and it's got real value because it's almost exponential. And so how we discuss the advantage is debated. And this comes up in the real world setting. I'll give you an example. A lot of the quantum machine learning work that goes on is about demonstrating only a quadratic advantage. And so we always have to be careful in studying what is the advantage quantum gives. Is there some reason to doubt it, something we're ignoring? And is the advantage that we show worth doing? And so these are the kinds of questions. Okay, so these are 4 cases of quantum advantage. I mentioned Shor's algorithm. At a foundational level, it's really that quantum mechanics is very good at finding periods. So we do a quantum version of a Fourier transform. So there's 3 steps in this. We take our input of qubits, we turn it to a superposition of all possible strings with equal weighting. Then we apply some arithmetic, which is exponentiation by squaring. It's a standard classical algorithm that we quantize, and then we end it by doing inverse quantum Fourier transform. The kind of the magic of, so in the public mind, often the discussion about the advantage of quantum computing, people talk about the parallelization, but that's only one part of the story. The second part about the arithmetic has no magic, but it turns out that converting arithmetic into quantum computing is where most of our effort lies. So it's a very boring part. And yet this is the part that we need to speed up to make quantum computers better, is we often spend a lot of our time trying to improve classical algorithms to do better arithmetic. And then the inverse quantum Fourier transform is key to finding periods. So quantum mechanics can be really good at finding periods. Mathematically, it's about identifying hidden abelian subgroups. And so, and this becomes important in breaking a lot of public key encryption methods that are based on factorization, discrete logarithm, etc. The second one is function inversion. This is the technical word for like a Grover search. And so subject to various assumptions about the assumption, we can run it in square root of the time. Time I'm talking about can be thought of as rigorous in the sense I talked about earlier. And this could be useful for computationally hard problems. 3-SAT is a satisfiability problem. It's the canonical NP complete problem. And we can reduce the time for that quadratically. So it's when people talk about using quantum computers for NP hard problems, like traveling salesmen, they're not looking for an exponential advantage typically. They're looking for a quadratic advantage. Adiabatic was motivation for early stage companies like D-Wave that did quantum annealing. And the idea was to make use of adiabatic processes. In the early days, 20 years ago, proposals were that adiabatic quantum computing was superior. This led to better understandings of continuous to discrete time. Adiabatic is considered equivalent, but one of the problems in adiabatic is we can prove equivalence of adiabatic quantum computing to other forms in the ideal, but the error correction fault tolerance doesn't map well. So there's still open problems with adiabatic quantum computing. And then sampling is important. This has become very popular in the past decade due to boson sampling. And so the idea of doing sampling, basically like making interferometers, send in single photons, look how they collide with each other and how they scatter onto photon detectors, can do sampling. A company like Xanadu, which is based in Toronto, does this. And so there is, some people have argued, like Alain Asper-Guzik in Toronto, that sampling problems can be mapped to quantum chemistry problems. This is still under exploration, but that's a kind of, it's speculative, and there is experimental work in companies related to sampling problems. Robustness that I talked about earlier is, so I talked about robustness earlier with input, output, and so on. Now I'm talking to you strictly about the quantum version of robustness. What we focus on is quantum computing people. And as I said earlier, we have to converge because, as we claim commercial, we do have quantum computers and they do work in the sense that they compute. They might not be advantageous yet, but we really do have quantum computers out there. Over time, we need to converge what we call robustness with the classical computing, and that's happening very fast. So in the quantum world, we care about error correction. And with error correction, we'll typically say, don't just send the qubits in, put them into code spaces. So we embed our qubit string into a larger qubit string that is highly entangled and is somehow protected against what we believe that the errors are. And then we periodically perform measurements as the computation is taking place, detect, and then correct the syndromes. Strictly speaking, we don't have to periodically interrupt. We can, just like in reversible computing, we could move all our error correction to the end, but that would take more qubits. So practically, we would rather interrupt. And then obtain signatures of errors. And the idea is that our error correction techniques are based on coding theory And the idea is that we need to be able to measure errors, but learn nothing about what the state is. Otherwise, we would decohere the system. And theoretically, it's actually not so hard to do this. If you learn coding theory, it's a lot of what we do is mapping in a not hard way standard coding theory into quantum coding. In the practical world, it's extremely difficult because we have to use lots of qubits and demonstrate the advantage. And so experimentally, error correction is in a very primitive stage, theoretically very advanced stage. Fault tolerance goes beyond error correction. It just says, things are not working perfectly, and you add more qubits, you add more gates, you add more measurements, everything is faulty. And so fault tolerance is that, as you try to fix your system, don't make it more broken than it was. In current stage, the emphasis is on noisy intermediate scale quantum, which is called NISQ, N-I-S-Q. And so the stage we're at in commercial quantum computing is all these companies are saying, look, we're not going to do any error correction or fault tolerance. We're just going to push our technology as far as possible, mitigate errors as much as we can, and hope that we can make things big enough to deliver an advantage. And John Preskill, a professor at Caltech, and also now a 1 day a week appointee at AWS, Amazon Web Service, is the person who introduced the NISQ concept. So a lot is being done, but right now in the field, everybody knows that NISQ is not delivering what's needed. And so the huge effort, and certainly companies that contact me about hiring people, all are saying we need to go post NISQ and put error correction and fault tolerance in, but in a way that works for the companies, not in the very theoretical way. NISQ achieved its pinnacle with what used to be called quantum supremacy, and then I think some American scientists and others got together. They wrote a Scientific American article and said supremacy evokes concepts of white supremacy, and that's a bad thing. And so the word supremacy is now stricken from American journals, magazines, etc., and it's referred to as primacy. So so we have quantum supremacy in much of the world and originated in the US, and then quantum primacy is now the dominant term. And the idea of quantum primacy, I'll say, is that the quantum computation solves a problem better than every alternative existing today. Google claimed that a couple of years ago, and then IBM had a blog that said you didn't get there because if we wanted to, we have a computer that could simulate your 53 qubit machine. But in recent times, there was results out of China, published 2 back-to-back papers in Physical Review Letters, and recently Xanadu and Toronto have pushed things well beyond. So I think most of us accept that we're in this quantum primacy realm, but the way to know it is you kind of have to go through these arguments saying, what would I do with all the computers on the earth today? Could I solve it? And these are known as spoofing attacks. And so the belief of whether we've reached this or not comes down to beliefs about how well we could harness existing resources to compete. But anyway, that was the pinnacle of NISQ, and now we're on the cusp of going to error-corrected fault tolerant. Okay, so now about building quantum computers, and here on the right of the title, you can see 10/CR58. So that's a short book I wrote about 5 years ago. It's now I would say quite out of date, but it covers the basic concepts. It's only 25 pages long. It's free. So if you want to go there to read it, you can. Now your question is, what do I do with this 10/CR58? So DOI.org is a public service. It's digital object identifier. They run a hash service. So it turns out that every DOI can be shortened to 10/something. And the something is no more than 6 alphanumeric characters. So if you go to DOI.org and type that in, then it should work, and out pops that book. I'm not trying to promote the book. I'm more fascinated by hash functions. But anyway, that covers a lot of the concepts that I said here. Does it in a general way. It's not deep into the physics. So there's different platforms to build quantum computers. And I just made on the list some of the platforms. Often it's called architectures in physics literature, but they're not. Computer scientists, software engineers don't think of these as architectures. So I prefer the word platform. One is photons, and then there's many ways to do photons. There's squeezed light approaches, which is done Xanadu in Toronto and a group in Shanghai in China as examples. There's also the discrete version using It can be polarization, time bin, path-based, which way a photon goes. Probably the leader in this area is Psi Quantum, which is in the Bay Area near San Francisco. There's also other companies, Orca and United Kingdom and others. So photonic stuff is going strong. Photons, the photon companies are saying we can't really do good quantum computing at the moment, but you give us time and we'll be the first to get to 1 million qubits. So right now we're at hundreds of qubits and a depth of a dozen gates maybe, if we're lucky. And they're saying, we'll give you 1 million qubits and perhaps 1,000 gates. So photons want to catapult over. Magnetic resonance early on was like liquid state magnetic resonance. The first result in quantum computing that can be thought of as a computation was factorization of 15. That was done by IBM at Almaden in San Jose, California. And magnetic resonance lives on in diamond-based schemes and various others. Trapped ions is important. So Honeywell does trapped ions. IonQ was a startup. They're now a publicly listed company valued at over $2 billion. That was founded by Jungsang Kim and Chris Monroe. Both of them are now professors at Duke University in the US, North Carolina. And so they make use of Bell state generators. Remember I told you about the Hadamard and the C0 gate for quantum teleportation. So they're able to make Bell states. This ties in with the Sorensen-Molmer scheme for trapped ion quantum computing. So trapped ion quantum computers are commercial. They will do computations for you. Neutral atoms is really an up-and-comer these days. A lot of the neutral atom community was focused for a long time more on Bose-Einstein condensates, BCS states, simulating quantum matter. But now a lot of them are thinking more and more about quantum computing. So the idea with neutral atoms is to trap them one atom per site in a two-dimensional optical lattice, make use of used to be collisions, controlled collisions between atoms. Nowadays it's Rydberg-Rydberg interactions. And neutral atoms in the marketing space is like photons. Says we're not going to try to beat existing quantum computers, but we'll get to 1 million qubits and 1,000 gates before anybody else. So neutral atoms and photons are competing for, the fault-tolerant, scalable world. And then the semiconductor world is expensive, smaller. Many of them want to be able to somehow leverage off the investment in the silicon industry. One of the leading, well, actually two of the leading groups of the world are two competing groups at the University of New South Wales in Sydney, Australia, and they do things like embed phosphorus into silicon and then make use of hyperfine interactions to control the electrons that can interact with two neighboring phosphorus, make 2 qubits in that way. Superconductors are currently the lead in commercial quantum computing. Companies like Google, IBM, D-Wave, Rigetti, and many others are working with superconducting quantum computing. And the idea there with D-Wave is more flux-based. So the idea is that you make a loop, and if you make a loop of current, it creates a magnetic field that could be up or down. They can make superpositions of up and down flux. But most of the work that goes on now is transmon related. These are Cooper pair boxes. So the qubit can be thought about whether a Cooper pair of electrons is on the left or the right of a junction. And then the hybrid semiconductor superconductor, the idea that we can put a superconducting wire onto a semiconductor, is where Microsoft's bet is. And this is building Majorana fermions. And so where Microsoft has been working is in creating topological quantum computing through layering superconducting wires on a semiconductor. This has been quite dramatic lately. I don't know if people know, but there have been various retractions of papers from Nature and so on. And so there's the field is abuzz because there had to be some retractions of papers to 5 years ago. And so where this particular field is going is going to be interesting. And then there's various implementations. Most of the companies are doing gate-based. Measurement-based is, I mentioned Psi Quantum as an example in the photon world. So they're going more to measurement-based, same with Orca. Adiabatic quantum computing is the foundations for D-Wave and the whole quantum annealing work. But adiabatic has problems, so not everybody it's kind of dangerous to embark on that because there's still theoretical issues. Topological originally was proposed as a way of avoiding error correction because things would be topologically protected. Gradually, people discovered that if you protect against an error and an error happens rarely, you can't get rid of it. So the same thing that protects you from error also stops you from fixing errors. So topological has some issues to go through, and robustness issues that are dealt with. And I think, I know I'm almost out of time. Yeah. So this is my last slide, and I'll just show you some pictures and give you some ideas. The upper left is the magnetic resonance, NMR, nuclear magnetic resonance. So this represents how Ike Chuang, now at MIT, co-author of that, Nielsen and Chuang, his group at IBM Alma did way back, factorized 15. The idea is you take a liquid, you have some molecule with carbons and fluorine and various other things, and then the qubit was written onto various nuclear states. And then you can see a Helmholtz coil horizontally that creates a DC electromagnetic field that lifts energy degeneracy in your qubits and does it in a way that each qubit, each nuclear qubit has a different energy splitting. And then vertically, you can see the coil that creates an AC magnetic field. I'm just mixed up right now between which is the AC and which is the DC. It's probably the other way around. So yeah, okay, I'm not going to say anything. I think I could be recorded, so I'm not going to say something stupid, but one is AC, one's DC. And then the AC magnetic field is just to move in and out of resonance with the qubit you want to flip. And then there's a scheme for doing 2 qubit operations. And on the right, you can see Honeywell's ion trap quantum computer. And so they make use of ions. There's different types of ions that are being used. And so typically they're alkali earth ions. So when they're ionized, it's effectively one outermost electron. So you can think of it like a hydrogenic atom. But there are efforts going on with ytterbium and strontium that are not alkali earth. They have other advantages. And so there's still investigations about which ion and even whether an alkali earth is the better choice. The lower left is a famous golden chandelier of IBM. So this is superconducting, and so the superconducting chip is at the bottom, and this golden chandelier goes into a dilution refrigerator, and then the stages as it goes down is really interesting. It's about making use of gold wires to be able to control what goes on at the bottom. And you have this problem where you need electronic controls that go through orders of magnitude change of temperature in a scale of centimeters. And so even even what you think about as electronics can be very complicated, nonlinearities, all kinds of things can come in. So in these systems, it turns out to be interesting just to look through the electrical engineering and ask whether what you think you're doing in the cold system is exactly what you're doing. And how do you characterize when you can't put that many instruments inside your fridge? This here is Cold Quanta, is an American company. So this is an early device they have for neutral atom quantum computing. And this nice rainbow colored diagram is PsiQuantum's, one of the pictures I just got off the website for PsiQuantum. I'm not actually sure if it's a picture of their instrument or marketing tool or some media capture of it, but that's the most popular image that comes up. So those are examples. If you want to know what a quantum computer would look like, this gives you some idea. No quantum computer would be like our laptop. You're not going to carry it around. So the way we're looking at quantum computing these days is it would live on the cloud, and it's all about cloud access. So I'm going to summarize by just saying that, so what I've covered here is the range of, I've tried to help you see what a computer is, at least from my perspective, the bridge through reversible computing to understand what computers have to do, the idea of universal quantum computers, the question of resources, time, space, etc. It's important to count them. In my view, it's important to assess the resources end to end, from classical bits in to classical bits out, to really determine how good a quantum computer is performing, how good a quantum algorithm is, the practical considerations, the current state of the art, that we're in the NISQ era, but we're about to move out, and examples of real world commercial quantum computing. So thanks for letting me talk about this, and I'm ready for questions.
Thank you so much, Barry, for this very deep talk. and very intriguing. So questions, please. We have a question in chat. Barry, can you read this or shall I read for you?
Yeah, I could, do you see my chat when I click that? Okay, I can read it. So what's the importance of topological materials in quantum computing? Can Weyl fermions be qubit candidates? What do you think about it? So that one, yeah, I don't really know the answer. The topological materials, of course, are extremely interesting. In quantum computing, we have to be able to perform gates, etc. We do have, I mean, in order to understand like our Majorana fermions that we want to use, we'll make use of, you know, models that are related to topological materials, Kitef type chains, etc. But the answer is I don't know, because we have to go all the way from topological materials to implementation, quantum computing. So I can't give you a satisfactory answer. I'm sorry about that. I'll go through the next one in chat, and then I see Oscar has his hand up. So next one was, as a career advice, where do you see the future of quantum computing research? Mathematics, computer science, or physics? Will physicists be alienated? Okay, so that's a good question. I'm going to give you my own sociological view. First of all, you know, I kind of think that a lot of fields branched out of physics. So, you know, if you look at 19th century mathematics, you know, it was physics questions that led to, you know, some statistics research, some mathematics, curvature. You know, there were thoughts about physicists. So I think there wasn't really a physics discipline per se a couple hundred years ago. And then you look at areas like electrical engineering that have grown out of physics and so on. So I tend to think of physics as the, you know, a fruit-bearing tree that we physicists are able to adapt and move into other areas. And the richness of the 21st century research is very interdisciplinary. You know, for me, even doing some basic physics, I'll often think about, you know, information theoretic concepts, you know, and actually I'll raise a point that Richard Feynman, Nobel laureate in physics, once asked whether the answer to the universe will come out of an equation, like a grand unified theory, or whether it's going to be like a cellular automaton, you know, whether we would essentially pose it as a computational question. And his whole interest in quantum computing stemmed from questions about simulating the universe. So the answer to your question, will physicists be alienated in quantum computing research 10 years from now? I think not. I think that if physicists are prepared to adapt to these kinds of questions, physicists are a key part. On the other hand, it's perfectly reasonable to stay focused on hardcore physics topics, because there's all kinds of physics questions that are emerging. Even the robustness requires us to understand noise better. So open system effects, as an example, need physicists. So Alikram, can I pass it back to you as chair? And I see Oscar with his hand up.
Thank you. I can ask my questions if nobody is asking. So basically, thank you so much for this beautiful talk. I am happy to see that your approach and definition of to quantum computation has a very broad perspective that reminds me of the resource theory, that your definition of complexity can be found in biological processes that take some advantage in quantum transport, and also energy processes in thermodynamics. And what we know from resource theory approaches also that when you want to take advantage of these resources, you hit a critical point, and getting more and more resources, eventually the advantage starts to drop. So this is known as the microeconomical law of diminishing returns. And we have seen this a lot of examples in biological systems, chemical systems, and so on. So from your perspective, then, should we expect that we will hit also some barrier before getting this ambitious millions of qubit goals, and then start to lose advantages of quantumness? Or I wanted to hear your opinion about that.
Yeah, so really the basic question you're asking is whether there's some fundamental limit to quantum computing, because at some point, you know, really accounting for resources will get too expensive. There could, I mean, it's very interesting. So I can tell you, what was it, about 15 years ago, in Canada, we have some organization that just supports high-level private meetings to have big kind of questions come up. And so at that time, we invited top people in the world to a meeting. And they were all the ones that said something like, there's a dead end to quantum computing, that quantum computing, for whatever reason, can't work on large scale. It could be because there's physics we don't know. It could be because, if you get too many resources in one place, it'll make a black hole. It could be that, the limits of the mathematics for infinite dimension don't work well. And we had them all there. And in the end, at the end of the meeting, we concluded that, they raised interesting points, but we couldn't see the dead end. And so what you're saying, Oscar, it could be there, but I wouldn't know how to formulate it. The only dead ends that I know is that the universe is finite, so we can't, well, maybe it's finite. If the universe is finite, there's a limit to how big we can make a quantum computer. And another one is if we put too much information into a local region, we would probably, the information has a physical realization and we might get swallowed into a black hole. But the part that I take, the part of what you say that I find especially interesting is the whole resource theory concept, that in the end, in order to analyze what's capable, we really need to get the mathematical aspect of the resource theory right and get that clear. And what you said about the connection to biological systems, I think is important. I think I have a paper on the archive. I don't know if I put in the archive, but we call that evolutionarity. So we're actually, working on things like not quantum, but it's the resource theory behind evolution. And of course, mathematically, it's discrete dynamical systems. So I don't know if I covered it, but you raised a point that has a lot of deep roots to it. Oh, I'm over time.
Thank you. Thank you so much.
Okay. So
more questions, please.
I might have to go. I have another thing I've got scheduled.
Yeah, sure. So thank you so much.
Thank you very much. It's been really great. I'll just take a quick look at the, oh, thanks. Okay. And then, yeah, if I see questions, but if anybody wants to contact me privately, I can respond.
Yeah. Thank you. But we will be waiting for you next week on Monday again at the same time.
I'll see you then. I got a lot of work to prepare that.
Forget to come, please.
Okay.
Bye-bye.
Okay, thank you.
Thank you. Bye, everyone.
Bye.